Alright, so now let's talk a little bit about, make sure that we understand what the physical meaning of the error is. Okay, so if we have this data set here and we have some data points here and we fit our line to these data points, this is the error term here. So this is our YE, that's the error, that's the Y estimated by the model, and then this over here, this is our YI, and this is the actual measured data, and this is the error. And so what we want to do in regression is we want to make sure that we're actually getting somewhere by fitting a line to the data. If we have some data like this, so say we have some data like this, do we really gain anything by fitting a line to this data, or should we really just look at this data and take the mean of the data? That's not a very good example, so maybe we should take the mean of the data. Okay, so really, which one of these is better? Okay, and certainly we can minimize the error and fit a line to the data, but then what we really need to know is by fitting a line, did we really do any better? Did we really do any good? Okay, because we can do linear regression on any data set and get some slope and intercept. But the question is, does that describe the data better? And it turns out that we can actually find out if we have fit the data better using some basic statistics. So I'm not going to go into the background of statistics. All you really need to know is that there's a term that's called ST, and that's called the sum of the squares. And for our case, we call this the sum of the squares of the error, which is basically yi minus y bar, where y bar is the mean of the data, or the average. Okay, so this is at the ST term, and then this would be the total sum of squares, and we use this term. Okay, this is the total sum of squares. Okay, and we use this in the definition of the standard deviation. Okay, and we'll call this standard deviation of the y data, and that's just equal to the sum of squares ST over n minus 1. Okay, and in this class we don't really go into statistics, but just so you know, this n minus 1 is basically the degrees of freedom. Okay, and basically we have n minus 1 degrees of freedom because we found one thing that's true about the data, and that's the mean. Okay, so when we use the mean, then we have n minus 1 degrees of freedom, where n is the number of data sets, the number of data. Okay, so that's all I'll say about that, but that's where that comes from. Okay, so there we have the total sum of squares. This is the standard deviation. Okay, and we have the variance, and the variance is just sy squared, which is the squared value of the standard deviation, and it's just st over n minus 1. Well, if we use the definition of the total sum of squares, we can rewrite this as the sum of yi minus y squared over n minus 1, and that's our variance. This can also be rearranged to say sum of yi squared minus the sum of yi over n over n minus 1. Okay, and so basically we can use these concepts to say if I have this data set here and I have these data points, we can take a look at the total sum of squares of the regression values versus the total sum of squares using the mean. And and define an R squared value. So what we do is you've heard of the R value. The R squared value is equal to ST, which is the total sum of squares, minus SR, which is the total sum of squares of the residuals, over ST. Okay, and here SR is similarly defined to SE, but it's basically the sum of yi minus y bar squared. Oh, I'm sorry, this is ST from before, and then SR is when we replace this y bar with, instead of using the mean of the data, we use the model, which is a0 plus a1 times x of I. Okay, so our SR, the total sum of squares of the regression, is yi minus a0 minus a1 xi squared. Okay, and if you see this, this is also the same as ei squared. Okay, so what we're basically saying, what we want to know is if we fit a line to this data, okay, are we any better than if we were to fit a line over here? And the way we do that is we basically look at these squared errors and we look at how well they explain it. And so here, if we get some mean like this, where the data is distributed about this line, and that's larger than the distribution around this line, then we can say that this is a better model. And that's what this R squared value is. And I think that's enough for us to say about that. Okay, and so as you can see, if SR is equal to 0, then R is equal to 1. R squared is equal to R is equal to 1. Okay, that basically says if SR is equal to 0, then that means the line perfectly fits the data, because yi minus our little model of the data is 0. Okay, and so then you'd say the line explains the data. Okay, if ST is equal to SR, then R squared is equal to R is equal to 0. And this basically says that the line explains nothing. Okay, the line explains nothing. Okay, in other words, if ST and SR are equal to the same thing, then we don't really gain anything at all by adding these coefficients. Okay, and it would be almost the same thing as if we had some data here, okay, and we took this value and we got an ST, and then we took the line fit to the data, and they actually became, that would be SR, and they were the same thing. Okay, and so that's what this says. So we have two extremes where the line explains everything or the line explains nothing, and that's where we get that R value. And this R value is called the coefficient of determination. Okay, and so if r squared is approximately equal to 1, you say yes, the line explains the data. Okay. Alright, so we'll stop here. Please send me an email if you have any questions or if anything's unclear, if you found any mistakes in this note, and I'll be happy to address them. Thanks.